Wow, it's a crowd. I'd like to thank everybody for coming. I really appreciate all of the attention. This is really nice. I'd like to thank Rui for inviting me to speak. So today I'm going to talk about quantum symmetry, and I'm hoping to keep this really down to earth. So if you have any questions, please stop me. I can scribble stuff on the board. Please let me know. So this whole talk is based on the notion of symmetry. It's appeared everywhere. It rules the universe. It appears in art and music and science with molecules. We've seen symmetry since we were born. This is probably the oldest mathematical notion. Particularly in art, some might say that a face is more beautiful the more symmetric it is. But I don't really like that notion of symmetry because I would have to choose between my two dogs. I would have to choose who is more beautiful, Mr. Mischief Maker or Dr. Boom Boom. So in a more mathematical context, where do we first see symmetry in undergrad? So groups, one can say, has arisen from axiomatizing the notion of symmetry. So given an object X, what is the symmetry of it? A symmetry is just an invertible, property-preserving transformation from X to itself. That's what a symmetry is. So if we were to take an object X and collect all of its symmetries, it forms a group. So like suppose that our symmetry is a butterfly, for instance. We see that the butterfly emits a really nice symmetry along the vertical axis. And if we were to collect the two symmetries, namely keeping the butterfly alone and flipping it, the collection forms the group C2. If we were to take three cups and were to rearrange them in any way we like, the collection of symmetries forms a symmetric group on three letters. And if we were to take a real two space and keep track of all the rotations and dilations and translations, this corresponds to the group GL2. Okay, so we've all seen this before. But in order to get at what a quantum symmetry is, again, we're going to keep this geometric picture in mind and look at symmetries of affine varieties. So what is an affine variety? Basically, it's just a zero set of a finite number of polynomials. Okay? So, for instance, if we take the affine variety in real two space and look at the equation x squared equal to y cubed, we have that this equation cuts out this nice cusp here. Okay? And just by eyeball it, we can tell that the only symmetry that this cusp emits is just by sending x to its negative. Okay? So the collections of symmetries of this nice cusp, again, forms the group Z2. Okay? So we can think about symmetries of affine varieties in general just by taking a set of finitely many polynomials and a polynomial ring, cutting them out, looking at the shape and seeing how can I rotate it and translate it and stretch it back onto itself. All right, so we want to make this more rigorous. So we should probably work in the category of affine varieties. All right, so we pick our favorite affine variety, like a cup, a space, or swirl, or whatever you like, and you ask, what is the symmetry of it? It's just going to be a group action in the category of affine varieties. Okay? So a group, this group has to be an affine variety, and it also has to be a group, meaning that it should probably be a linear algebraic group. All right, so what exactly is that? It's a variety, but it also emits a multiplication map and an identity element and an inversion map, which are morphisms in objects in this category, just like you would expect out of a definition of a group. Okay? And this also satisfies group axioms, like, for instance, you take any element you like in your group and you multiply it by the identity element, you should get the element back. You take any element you like and you multiply it by what happens under the inversion map, and you get the identity, and then you have associativity. So this is pretty well understood. But say, for instance, you have a geometric object that you can't really eyeball the symmetries of, like a cusp. Like say, for instance, you were working in 4 space or 5 space. I mean, maybe you can visualize this, but I can't. So what's really advantageous about this setup is that we can push this over to the algebraic setting. And instead of working with affine varieties, we can work with their coordinate rings instead. Okay? Any questions so far? No? Okay. Okay, so we're really going to exploit the relationship between classical geometry and commutative algebra to think about symmetries. All right, so what do? We send an affine variety to its coordinate ring. It's a contravariant functor. So all of these maps over here basically get flipped. So instead of looking at the action of a group on a variety, this turns into a coaction of the coordinate ring of the group, on the coordinate ring of the variety. So for instance, like if X were just affine 2 space and G, let's say this is over C, and G, let's say, is SL2C. I mean, we could really think of this as the complex 2 plane. Then the coordinate ring is just going to be the polynomial ring of 2 variables. And OG, well, this is going to be, well, how do you form SL2? You take 4 variables, EIJ, where I and J range from 1 and 2, and you just cut out the determinant equation. That certainly is a variety, equal to 1. Okay, so these gadgets, because they belong to the category of commutative algebras, they're commutative algebras, but this OG actually comes equipped with a lot more structure. Because G over on the affine variety side omitted the structure of a group. It has a multiplication, an identity, and an inversion map. Its coordinate ring actually has a lot more structure. It emits a co-multiplication, a co-unit, and an antipode. And these gadgets play well together, and they satisfy so-called Hoff algebra axioms. Okay? So basically, geometrically, the action of an algebraic group on a variety corresponds to a coaction of a commutative Hoff algebra on a commutative algebra. Okay? All right. So again, this setting is really advantageous if you're working with varieties that you can't visualize, like something in 4 space and you're trying to analyze, I don't know, the analog of a cusp in 4 space, and you want to know what are the symmetries of it. Now, what if you are working with objects that you really can't see? Let's say a quantum variety. So if you were to take this framework and translate it over to the context of noncommutative geometry, well, you can't exactly draw quantum varieties. This is nonsense. You really do have to work algebraically. And so instead of working with coactions of commutative Hoff algebras on commutative algebras, you're really working with the non-commutative versions over here. Okay? All right. So that is the basic setup of quantum symmetry, the basic setup. So I should probably be a little more specific and tell you what a Hoff algebra is and all the decoration that comes along with it to make your theorems nice. So what is a Hoff algebra? So it's an algebra, meaning that it's a vector space that comes equipped with a multiplication and a unit. It's a coalgebra, same vector space, and instead of having a multiplication, you can split apart elements. That's a coalgebra structure. And then you also have this version of inversion, which is the antipode map. And all 3 of these gadgets play nice with one another. There's a lot of compatibility axioms, and I could give the proper definition, but then I think it would take the whole board, maybe. Like all these things interact with one another. But the Hoff algebras that we really want to keep track of are the ones that, as an algebra, are commutative. They're called commutative Hoff algebras. Or as a coalgebra are co-commutative. These are called co-commutative Hoff algebras. So some really classic examples. For instance, if you were to take a group and you were to look at group algebra, this is a nice co-commutative Hoff algebra. Why? Because by definition, co-commutativity means when you apply the coproduct and you were to flip along the tensor, you get back what you started. So you have some symmetry about the tensor product. Also, if you were to take a Lie algebra and look at its associated associative algebra, namely the enveloping algebra about it, This is a nice co-commutative Hoff algebra because you have a nice symmetric coproduct here. Okay? Now, if you happen to have that your group and your Lie algebra are abelian, you get that these Hoff algebras are also commutative. And as we saw a slide ago, the coordinate ring of an algebraic group is a nice commutative Hoff algebra. So the reason why we want to keep track of these is because these really correspond to classic symmetries. Groups act by automorphisms, Lie algebras act by derivation. This is classic symmetry. When we get away from commutativity and co-commutativity, that's when we're really talking about quantum symmetry. Okay. Any questions? It is getting warm in here. Oh, everybody's going to go to sleep. Please don't go to sleep. Here's some cookies. All right. Okay. So what exactly do I mean by an action? What do I mean by action? So I have a Hoff algebra acting on an algebra. So what that means is that your algebra is going to be a module, right? I mean, this takes care of the vector space piece. It's going to be a module. But you also want the other components of your algebra structure to be morphisms, H morphisms here, right? So in that case, we say that A is an H module algebra when you have an action of a Hoff algebra on an algebra. Now, I mean, this is pretty abstract to check, but there are actual equations to make sure that these conditions hold and their formulas are there. You don't have to remember them, but there is something very concrete to check here. Now, what about a co-action? Well, basically, I stick in the word co, and I flip all these arrows. So I'm just going to flash that really quickly. You got a co, and you got a bunch of arrows flipped, but you have a notion of a Hoff algebra co-acting on something. All right, but this probably makes better sense with some examples. So going back to our classic Hoff algebras, let's say, for instance, I have my nice algebraic group here, SL2, right? The 2 by 2 matrices with trivial determinant, and I wanted to take the group algebra of it. Well, we know that it acts on the coordinate ring of affine 2 space just by matrix multiplication, basically. You just take your first coordinate u, and you use the first column of your matrix, and that's how you get your action. It's a nice linear action since degree 1 stuff to degree 1 stuff, and similarly for the second variable. If you were interested in an example of something acting by sort of a derivation on affine, in this case 3 space, let's take SL2, which is probably the first example of a Lie algebra you've come across. You take the enveloping algebra of it, and you get a nice action of this universal enveloping algebra on this polynomial ring. So again, in order to check that, you actually have to go through these formulas, which can be a little bit of a pain. But I checked it, it's right. I checked it, it is right. There you go. Now, if you wanted an example of, let's say, a classical coaction, like we saw before when you had the algebraic group acting on a variety, and you looked at the algebraic version. Again, you could take your polynomial ring in 2 variables, and instead of having the group algebra act, you have the coordinate ring of this variety coact. Okay? And there's the formula for this. So this is pretty standard. Okay? Any questions? No, yes, maybe so. Okay. All right, so what do we mean by quantum symmetry? So really, roughly, what I'm going to do is I'm going to replace our plane with a quantum plane. I can't draw it. So what you really do is you replace the coordinate ring of the plane with the coordinate ring of a quantum plane. And this is sort of the standard prototype for the coordinate ring of the quantum plane. So basically all we do is, instead of requiring that our variables x and y commute, we say, okay, now they're going to q commute, where q is a non-zero scalar. So there is a very rigorous process how to go from classical geometry, commutative algebra, to non-commutative algebra, quantization, deformation, something like this, or sticking in q's in a very clean way. but this will be the gadget that we work with. This is going to be the object that we take symmetries of. All right. Now, you might think, well, why do I need to work with Hoff algebras in order to analyze the symmetries of this polynomial ring? And I don't have a slide on this, but basically the reason is this. So if I were to take this algebra, so it's generated by two true generators, and they Q-commute. Okay. Let's say that I'm interested in only linear actions. So linear actions, meaning it preserves degree. So preserving degree or grading. Sending degree 1 stuff to degree 1 stuff. If I were to take, let's say Q equal to 1, then this is the polynomial ring. And you have the whole group GL2 acting on this ring. Okay? It's a large, large symmetry group. But as soon as you get away from plus or minus 1, you only have diagonal matrices acting. So only 2 by 2 matrices of the form like so. So the number of symmetries drops as soon as we get away from the classic case. So in order to really talk about this algebra is beautiful and it deserves some notion of symmetry, so we should really think beyond group actions. Okay. All right, so to go from, I guess, classical symmetries to quantum symmetries for this algebra here, so we can take our classical setup. Let's say that we have the coaction of this algebraic group OSL2, and it's going to coact on this polynomial ring again by sending U to the sum of tensors, and V to the sum of tensors. And basically what we can do is get into quantum symmetry pretty fast by considering the Q version of OSL2 here. So if you notice, if you stick in Q equal to 1, you get the polynomial ring, because all your EIJs commute, modulo the regular notion or regular equation of the determinant here. Okay? So, and there's a very careful process on how to stick in Q's. This is derived from our R matrix, blah, blah, blah. But in any case, you can take the semi-classical limit and get back to this picture here. And also, so the coproduct is the same, the co-unit's the same. The antipode changes a little bit. We have to stick in a Q there. And we can even use the same coaction to get a group, to get a coaction of this quantum or this non-commutative Hoff algebra on this non-commutative algebra here. Okay? So upshot is sticking Q's in a careful way. We get from classic symmetry to quantum symmetry really quickly. All right, so I do non-commutative algebra. I like non-commutative rings, and I don't really want to give a talk based on you take a commutative picture and you stick in Q's and then you get a non-commutative picture, or you have a commutative result and you do some alterations and then you get a non-commutative result. There are interesting non-commutative rings that have nothing to do with commutative rings. They're purely non-commutative, and they're wonderful to play around with. And some examples of these non-commutative algebras are path algebras of quivers. So what is a quiver? A quiver is dots and arrows, basically. It's a directed graph. I don't know why it's called a quiver. I don't know who called it a quiver, but that's the standard name. So what exactly is it? Again, it's just a directed graph. And how do you actually form an algebra from it? Well, it has as a k-vector space basis paths of the quiver. So like made up of the vertices E1, E2, and let's say the path A, B, A, B, A, B, A, B. That is a basis element. And how do you multiply these basis elements? It's just done by concatenation. So like, for instance, E1A is equal to A, and that's an element in your algebra. And AB makes sense, so that is an element of your algebra. But AA doesn't make sense, so we set that equal to 0 in your algebra. Okay. So what's really nice about this algebra is that you could just look at the quiver and pick off the classic symmetry right away. We see that this quiver emits a Z2 symmetry just by swapping the two vertices and swapping the two paths. So it emits a Z2 action that takes G and it swaps the two vertices and it swaps the two paths. So we see that this path algebra emits a nice classic symmetry, but also emits a lot of quantum symmetries. So how do we do that? Well, we take a nice Hoff algebra that has sitting inside of it Z2. So we have this nice Hoff algebra here. It's generated by an element G and X, where G is so-called group-like. It has the group algebra of Z2 inside, and it's also generated by element X, which is skew primitive. It looks like a primitive element. It looks like something that will come out of a universal enveloping algebra, but messed up because of the G here. And so we get an action of this really nice Hoff algebra, which it's probably one of my favorites because it's only 4-dimensional and it's not commutative and it's not co-commutative. They want to come in? Oh, hi. Hello. Okay. Oh. Okay, so then you have a Hoff algebra that's like an extension of a group. And so you take this group action, and then all I have to do is tell you, okay, where does the X send vertices and arrows here? And as you can see, this action depends on this parameter gamma here and another parameter lambda here. So you have one action, one classic action, extending to infinitely many, 2 fields worths of classic or quantum symmetries here. So for instance, I mean, taking that algebra over there didn't have a whole lot of actions of a group, but you can get to actions of Hoff algebras pretty easily, and you get lots of quantum symmetries as a result. Okay, so, all right, what am I even saying? What's the point? The main question is this. If you have a quantum object, whatever that is, you take the noncommutative algebra associated to it, like a coordinate ring, and you ask, what are the genuine quantum symmetries? What are the Hoff algebras that act on it that don't factor through the action of a group or a universal enveloping algebra? When do I have genuine quantum symmetry? So for instance, by classical Hoff algebra, I mean group algebras, universal enveloping algebras, coordinate rings of algebraic groups, things that are commutative and co-commutative. We want to stay away from that. Okay? So this is a pretty vague question. It's pretty tough. So what do? You throw a lot of hypotheses at it to make it more feasible. So I want to go through some of those hypotheses along with highlighting some classification programs pertaining to this. So some useful hypotheses. So there are 3 types. I can impose conditions on the Hoff algebra, I can impose conditions on the algebra that I'm acting on, and I can impose conditions on the action itself. So I wanted to, those are the 3 spokes. Okay, so the first thing I could do is I can say, all right, as a vector space, my Hoff algebra is going to be finite dimensional. And you might think, that's too much. That's too much, it's too strong, it's stupid. But it's not, because actually the classification program for finite dimensional Hoff algebras is extremely active. It's been going on for over 20 years, and it's not anywhere close to being done. So this is actually a pretty mild hypothesis. But how does this program work? It sort of goes in 2 tracks. So you can impose a further condition, semi-simplicity. Basically what this means is as an algebra, it's semi-simple. Or you can impose this condition called pointedness. So what's pointed, so a Hoff algebra is pointed if you take every simple comodule and it's one-dimensional. So this is sort of a module theoretic condition, and this is sort of a co-module theoretic condition. And what's really interesting is that, at least in the literature, in order to classify semi-simple Hoff algebras or pointed Hoff algebras, they really depend on two totally different techniques. So on a semi-simple side, there are really group theoretic techniques that are used, like normal extensions and CELO theory and just things that you learn in abstract algebra, for sure. On the pointed side, a lot of these classification results depend on leaf theory, like there's Cartan data associated to these Hoff algebras. Your small quantum groups appear in deformations of. So these are like two different beasts, and they only really intersect for group algebras here. So if you were to impose some conditions, you go down one of the two tracks. You don't go down both. Okay? So some of the names associated to this program are Hans Snyder, Nicholas Andrzejewicz, and they're two camps of students and postdocs. And again, it's been going on for a really long time. Okay. Usually characteristic 0 helps. All right, so what about the algebras that we're going to act on? So polynomial rings, these are cool. We probably want to keep these. We should probably keep these gadgets here. These are nice. They act like polynomial rings. But what do we mean by nice? Exactly. So we can ask that the ring is homologically nice, meaning that it has a nice finite global dimension, or it has a nice injective dimension. It's Cazul in some sense. There are various different versions of Cazul. It maybe behaves like the coordinate ring of a Calabi-Yau variety, or skew version of that. So these are nice homological conditions. Or you might want to be a little more old school and ask that the ring is just commutative or domain, Noetherian, things that you learn in commutative algebra, or it even grows nicely. So if the algebra is graded, the vector space dimensions of the graded pieces grow like a polynomial ring or something like this. Okay? So again, homologically nice, tossing conditions, ring theoretically nice, you can ask for these. And there's a very, very nice program to classify the noncommutative algebras that behave like polynomial rings homologically. And these are called Artin-Shelter regular algebras, and more generally, or recently, skew Calabi-Yau algebras. Okay? And some leaders of that program, my advisor, Mike Artin, and Michelle Vandenberg, and James Zhang, and some other people. And I guess that program's been going on for maybe 30 years, 25 years. Something like this. So this Q polynomial rings included. I think this ticks all the boxes except Calabi-Yau. You get Calabi-Yau when Q is plus or minus 1, but ticks every box. All right, are there any questions? I'm just kind of flying through this. None? Nobody wants to play? Ask me questions.
What does K2 mean?
K2? I think that the, K2, the X algebra, if you take, xkk, it's generated by x1 and x2. Yeah, I think that's the condition. I think what's really nice about that condition is that, so for instance, some of these generalizations of the Cazul property don't behave well under tensor product and polynomial extension and OR extension. They created this because this does. And by they, I mean Tom Cassidy, and Shelton. Yeah. So once you have a K2 algebra, you can build a bunch more. Okay. Any other questions? Yeah.
Are you generally in characteristic 0? Or
yeah, it was fun. No, but no, okay. So, so the stuff that I've done in characteristic P has sort of been a means to an end. Yeah. But yeah, in general, characteristic 0. All right. So what about conditions on the algebra? So, all right, if the algebra is graded, maybe you want the H action to preserve the gradient. If it's filtered, maybe you want the H action to preserve the filtration. And these are nice conditions. There's also a version of determinant. So like, for instance, if I have G yeah, if I have this algebraic group acting on this commutative algebra, where G, it could be SL2 or it could be a finite subgroup of SL2. This is like a trivial determinant condition. There's a homological version of that for Hoff actions. And so sometimes we might want to impose that to get a version of a result for finite subgroups of SL2 acting on polynomial rings or something like this. Okay. And what is it? It's a map from, homological determinant's a map from H to the ground field, and it's trivial when it's equal to the co-unit map. Okay. All right, so I don't really want to get into this too much because it's a little technical, but it's there, we can use it when we need it. All right, so I should probably convince you that, how much time do I have left? I have to tell.
Another 20 minutes.
Okay, yes, I have to tell you I've done something. All right, so what results are there out there? So one set of results is called no quantum symmetry. So it's basically when you have an object and you know that the Hoff action has to factor through something classical like a group or Lie algebra or the action of an algebraic or coaction of an algebraic group. Okay, so just again to remind you, the classical Hoff algebras are groups, Lie algebras, things like this. And in fact, what we really want to keep an eye on are the co-commutative Hoff algebras because there's a really nice result by Cartier, Cosant, Milner, and Moore that says if you have a co-commutative Hoff algebra over, let's say, C, then H is just a mixture of a group algebra and a universal enveloping algebra. Okay, so co-commutativity is what we really want to keep an eye on. So if we're given an algebra and we have a nice Hoff action on it, we say that there's no quantum symmetry if this action has to factor through something co-commutative. Okay. All right. So when does this actually happen? I mean, this isn't really I don't know. This isn't really a result that one would want to shoot for, but we need to know when this happens. This happens a lot, actually. So if we were to take our algebra to be a commutative domain, like the polynomial ring, or the coordinate ring of that cusp that drew at the beginning. Pretty much a lot of algebras that you think of are commutative domains. And you were to take your Hoff algebra to be something semi-simple. Okay, so semi-simple as an algebra, you don't have quantum symmetry. So if you wanted to cook up some quantum version of algebraic geometry or something like this involving Hoff actions, you better stay away from actions of semi-simple Hoff algebras. You should probably go down the Lie theoretic track and work with pointed Hoff algebras instead. So in this, as you can see here, there are results in positive characteristic as well. So commutative domains don't really emit quantum symmetry if we stay in the realm of semi-simple Hoff actions. So one might think, can we soup up this result and get similar results for, let's say, quantizations of commutative domains, like the filtered algebras that sort of act like these guys? And that's true in a lot of cases. So if we take a Weil algebra or a ring of differential operators on a smooth affine variety, or universal enveloping algebra, or any other algebras that sort of behave like commutative domains, but they're quantizations of, we don't get quantum symmetry here. So any action of such a Hoff algebra on these types of algebras must factor through the action of a group. Okay? And we also have that for many of these skew polynomial rings here. Okay? So I mean, this is kind of a downer. I mean, it's a bummer. But the techniques are cool. That's, yeah, I don't know. I like it. I mean, some people don't, but I do. Yeah. All right. So we have lots of no quantum symmetry results. All right. So I do want to emphasize that these results aren't really unique to the algebraic setting. They do appear in other settings, particularly involving C-star algebras. And in that case, A is going to be the coordinate ring of something differeo-geometric, like a sphere or a torus or a certain manifold. And I don't really want to get into that too much. I just have a bunch of references at the end of the talk about this analytic setting here. So these types of results aren't new. And actually, this setting's older than the algebraic version here. Okay, so I told you there are a lot of no quantum symmetry results. I should probably tell you that there does exist genuine quantum symmetry for some algebras. And there are 3 types. I don't know if I'm going to have time to go through all 3 types.
May I ask, just with these things that you didn't want to talk about, are there analogies that let you sort of think, okay, if that's true in this case, then such and such thing is true in this case?
All right, so you mean here?
Yes.
So basically, how does it work? Yeah, so it kind of works this way. If there's no quantum symmetry in an algebraic setting, so there's not going to be any in the analytic setting. So sometimes I look at these papers to get an idea for examples of quantum symmetry, because if you strip away the analytic structure, you just have an algebra. Right? So that's how the relationship works. So they like these no quantum symmetry results because they know that these are examples that they should avoid. They also work with universal quantum groups, and these are things that Hoff algebras that act universally on these algebras, and they're quantized coordinate rings, but with a C-star algebra structure. Okay. Yeah. Okay. Any questions? Okay. Wrong way. All right. So quantum symmetry. So we have an algebra. We can think of it as like the coordinate ring of our favorite object, a cusp, a face of a dog, or I don't know, but a coordinate ring. And we want to know, if we have a Hoff algebra acting on it, we want to make sure that it doesn't factor through anything co-commutative. We have an honest quantum symmetry. So there are 3 occurrences of this, too, which I know. So one, I sort of started off, let me maybe go back to that. Can I do this? Oh, dang, I didn't push it enough. Here we go. Yeah, okay. Here's some genuine quantum symmetry here. Basically, if we set these parameters gamma and lambda equal to 0, right, we have that x is 0. That kills everything. So really, if gamma and lambda are equal to 0, then really I could just factor out the x. I get the action of kz2. So that is no quantum symmetry. But if I make gamma and lambda not equal to 0, this is a genuine quantum symmetry. It doesn't factor through anything smaller. So we have a souped up version of this for more general quivers. And that's work with Ryan Kinzer. Okay, did I push the button enough? No. Sorry, I have to keep. Okay, all right. So what quivers are we working with? They have to be finitely many vertices, no loops, loops are bad, no parallel errors. And what kind of Hoff algebras are we working with? The Hoff algebras that are pointed, that behave like small quantum groups, UQSL2, something like this. And we have lots of examples of quantum symmetries on such path algebras. So for instance, this quiver, the stuff in black, we can look at it and say, it emits an action of Z2. And we can also extend this to an action of the Sweetler-Hoff algebra that we saw before. We have very clean formulas. And the reason why I work with Ryan Kinzer is because he's really combinatorially minded, and I am not. So the clean formulas I really need him to work with me on this. So I was really happy to do that. I pushed the button. I'm holding these at the same time. So. Okay. Any questions on this? Yes.
So you said there's a Z2, and before you had in your example, it was kind of a family that depended on lambda and gamma, and when you set them both equal to 0, you recovered the classical Z2. So does it always work that way? Is there always a genuine group kind of?
Yeah. So attached to these particular Hoff algebras is a underlying group called the group of group-like elements, and that's going to act. And actually in these cases, the group of group-like elements is not trivial. It's not trivial. Actually, if it is trivial, these algebras would be infinite dimensional. Okay. Yeah. And so we get lots of parameters here for the Sweetler-Hoff algebra axioms, but then I would have to write 3 more slides But anyway, yeah, so there's classic symmetry hidden underneath. We just want to make sure that's not all we have. Okay, commutative domains. I told you if you went down the semi-simple path, no quantum symmetry. What if you went down the pointed path? Do you get quantum symmetry? And the answer is yes. I mentioned before that these pointed Hoff algebras depend on Cartan-type data. And here's some examples of these pointed Hoff algebras. Again, these are the ones that any semi-simple coalgebra is one-dimensional. That's the meaning of pointed. Or that the dual is basic, if you like. So you have like your small quantum group, UQSL2, twists of it, whatever that means, UQGL2. And these all act on commutative domains. They don't factor. In fact, they act on fields, which is probably the nicest commutative domain. So in this particular case, we call such Hoff algebras Gallo-theoretical because they act on fields. Ha ha ha. Okay. So these are really nice. And there's what's really cool is that once you have a Gallo-theoretical Hoff algebra, you can build more by taking subalgebras and tensor products. But you can't use any old construction to cook up more of these Hoff algebras here. Okay. And I'm going to skip that one. And lastly, I mentioned before that there are nice homological versions of commutative polynomial rings. Rings that have finite global dimension and have nice resolutions and things like this. And these were called Artin-Shelter regular algebras. And if we take the ones of dimension 2, global dimension 2, there are these. And there are also one more. This is called the Jordan plane. It comes from Jordanian deformations of something in physics that I don't understand, but I know these rings. So these are the only two Artin-Shelter regular algebras of dimension 2. Okay? And of course we have the commutative polynomial ring in here by taking q equal to 1. And we classify all of the finite dimensional Hoff algebras that act on these two algebras subject to this trivial homological determinant condition. Okay. So that was done in work with James Zhang, Ellen Kirkman, and Kenneth Chan. And from there, if you think about it, this is pretty much the start of a setup for a non-commutative Mackay correspondence. So what is that? I know I'm going to go down a rabbit hole, but like you, where does it start? It starts with a finite subgroup of SL2 acting on a polynomial ring linearly and faithfully. So we have a version of a finite subgroup of SL2 acting on a polynomial ring in two variables linearly and faithfully, so this action doesn't factor. So from there, this is sort of getting into the realm of noncommutative invariant theory, and we have a couple papers on a Mackay correspondence in this context. We also have other work on the invariant rings that appear in the setup, and also deformations of a version of the, I guess, skew group algebra that appears in this context. But these are really like two different talks, and I don't really want to go into too many details. But I have all my talk notes online. I'm happy to answer questions. Just email me, and I'm very, very happy to talk about that. Okay, so what now? If you like this stuff and you want to get into it, I mean, from what I see, there are several different avenues. First of all, one avenue is computation. Now, for commutative algebra, there are lots of wonderful programs like Maple and Macaulay and even GAP. GAP handles groups. There are lots of programs that handle non-commutative algebra and even group theory. For Hoff algebras, for non-commutative algebras, not so much. So if you can write a program to handle any of these computations, that will be glorious. If you wanted to cook up some sort of classification results, what do? You impose some conditions on the algebra. You can impose some conditions on what acts on these algebras, and you ask, is there a quantum symmetry? I mean, that basically is the game. If you don't like to be that down to earth and you rather think of this more categorically, when I say that an Hoff algebra acts on an algebra, what I mean is that that algebra is an algebra object in the tensor category of H modules. That's really what is lurking behind the scenes. So there should be a tensor category, fusion category, machinery to handle all this quantum symmetry business. And that's eventually where I would like to go with this. Of course, you can go orthogonally. You can make connections to other fields. There's a clear connection to functional analysis because that's where this kind of started, and geometry, as we illustrated, and maybe topology. And obviously, it would be nice to have applications to physics because the grants people like that, and you get money. And if you know anything about this, let me know because I need some money. And just Okay. All right. Well, thank you very much for listening. That's all I have to say. Thanks. I have lots of references.
Any questions for Professor Walton?
It's too warm for questions. Yeah.
Can you go back to the path algebra slide? Is it possible?
Oh yeah, I can push it. See, I can push it 18 times. I think. Oh no, I lied. Okay. Yeah, that one. Oh, the other one.
No, the one where you're the
one
results
where you
one.
exhibited the
The
symmetry.
results one.
That's 9 times 4. Okay.
There's fewer. Yeah.
Oh, I did it.
It's amazing. Is there any hope of classifying Hopf algebra actions on path algebras, or anything like? I mean, is it? I can't. Sorry, maybe I misunderstand. Did you completely classify actions on?
For these particular Hoff algebras, for these particular pointed Hoff algebras.
There must, I guess there's probably a notion, is there a notion of the Hoff, there's an automorphism group for a structure. Is there a notion of a kind of universal
Yes.
Hoff algebra action? Is it possible to calculate that for the path algebra of a quiver in general?
Yeah. That.
So you guys have done this in some set of cases, though.
No, I didn't do it yet, but there is definitely a notion. So that would be another bubble if I had another.
Is it something that's tractable to do?
Okay, so these okay. So really, there's not really a universal Hoff algebra that acts.
Mm-hmm.
There's usually a universal Hoff algebra that coacts.
Oh yeah. Okay.
So if you have a coaction, so it's like an action, but you just flip the arrows, and this universal guy, let's call it O, it depends on A. This is going to be, it has to coact on your algebra, and you want this diagram to commute. This Hoff algebra is typically huge. You don't necessarily know if it's finitely generated or presented. Mm-hmm. That depends on properties of A. For A being a path algebra of a quiver, that could be a good thesis problem. Yeah, that would be good. No, I haven't done it yet, but my mind is ticking. Okay, but so I've studied these guys for certain art and shelter regular algebras, actually. The algebras that behave like polynomial rings. Mm-hmm. And that was work with my postdoc, Xinting Wei. These are huge. These could be nasty. Mm-hmm. Yeah.
Professor Dodd, did you have a question?
Professor Dodd.
Can you tell us a little about the Mackay correspondence in the quantum case? Are there ADE diagrams, or what do you expect to see?
I just gave a talk about this 2 days ago.
Oh.
Yeah, and I have it here. Actually, can I use your computer? Am I allowed to do that? Can I go to my site? Oh, this is good press. Okay, wait, I have to look up my address. I don't want to check your email. Chelsea was horrible. Gave a horrible talk. Yeah, I just gave. So I put all my notes on my page. Yeah. Okay. Download. Download. What's a PDF? Come on. What happened? Where's your... Give. What happened?
Can you click on the on next to PDF, just slightly below to your left.
Uh-huh.
There, next button.
This one?
Yeah. Just yeah.
That?
I will should work.
Oh,
There
okay.
you go.
Okay, great. Yeah. What have you? Oh. Full screen. Oh my God. Oh, that's so much writing. Can you read that?
Yeah.
Oh my God. Okay, maybe I zoom in. Is that better?
Yeah, okay.
Can you read that? Okay, that's Mackay correspondence.
Right.
But it's an incomplete picture, so ignore it. So anyway, it's this web of objects that all depend on ADE diagrams, groups and singularities, and various homological, various categories of modules associated to finite subgroups of SL2, and the algebra that it acts on a polynomial ring in two variables. So if we replace our finite subgroup of SL2 with a semi-simple Hoff algebra, because we want to work with a semi-simple category, and we replace our polynomial ring in two variables with the Artin-Shelter regular algebra, global dimension 2, many of these directions go through. Namely, all the homological business we've done, the Mackay quiver we've defined. Unfortunately, we don't get a bijection between that bubble and this bubble, and we get other Dinkin diagrams that appear of type DL and L. Okay? We don't know this. The singularities, I have no idea how to handle that. I don't know what it means to blow up. Yeah. But, yeah. But yeah, we get type DL. So we get this guy, extension of L1, and then we get DL.
All right.
Yeah, these two.
Yeah, in addition to the usual.
In addition to those, yeah.
Oh, that's really interesting. Did you expect that, or was it a surprise?
We didn't expect anything. We just, just did it. Oh, that's what we got. That's weird. And we lose the bijection. So in the Mackay correspondence, you get for every ADE diagram, you get a finite subgroup of SL2 up to isomorphism, and vice versa. We have different pairs of Hoff algebras acting on algebras that correspond to the same diagram. Actually, a lot of them correspond to type A. So that's sort of unfortunate. But anyway, the homological stuff goes through really cleanly. But not too cleanly. I mean, we did work.
Yeah, cool.
I'm puzzled by the use of the word quantum. Can you explain why it should be there?
Yeah, I mean, I say that to attract people to come to my talk. No, but yeah, I mean, then usually I sneak off with like a physicist afterwards and ask, what does quantum really mean? So quantum, what it's really supposed to do, it's supposed to be the coordinate ring of a quantum variety, quantum object, maybe an object that you would pass through quantization and get this gadget. But I can't really give you a very rigorous answer on the spot, on camera. Maybe with a bit more thought I can. But it's very vague and it's not well defined. So yeah.
But in some sense it goes like to Alan philosophy of non-conclusive chunks.
Yeah. So you have some quantum object that you can't picture out, you can't visualize, but you can visualize the coordinate ring of it, the function algebra of it, and so you work with that. But whatever that quantum object is, I do not know. Physicists, they know. Yes?
In all your examples, you've divided by ideals with one generator, so you have codimension 1 varieties. What happens when you have higher codimension varieties?
Yeah, so I did that for simplicity.
Okay, that's what I was.
Yeah, so actually the result here, we only have it for dimension 2. So you notice the invariant ring is a hypersurface,
Yeah.
as we expect. And we get the same thing for the non-commutative picture. Oh, here it is. Okay. So here's a non-commutative picture. So we have that our invariant ring is a quotient of an artificial to regular algebra of dimension 3. So an example of that is a polynomial ring in 3 variable, and you quotient out by a normal element instead of a central element. So we have the same type of phenomenon in dimension 2. But even in the classic case, when you work with higher dimensional varieties, a lot of parts of the Mackay correspondence breaks down. So we didn't do that. Yeah.
Any other questions? Okay, let's thank Professor Walton.
Thank you.